Okay, we're now recording, and I'm going to do Introduction to Java. Okay. Slideshow. Introducing Java. Wonderful. So, what is Java? Well, it's a widely used programming language. Lots of stuff. The big one is applications on servers, right? So all this behind-the-scenes stuff, Java is widely used for that. And other things, large-scale data analysis, it's the last I checked is the default language for developing Android apps, and lots of other stuff. So if you're interested, here's a little article here from a couple years ago, Why Should You Learn Java? We talked some about that the other day, but the short answer is Java is widely used. It is likely to be widely used for the foreseeable future. It's a good language to know on its own merits. And if you want to learn other languages, it's a good starting point. For example, Java's kind of in the middle of this sort of complexity. So if you learn something like JavaScript, which I teach some of in IDS 3.13, JavaScript is in some ways like a greatly simplified version of Java. On the other hand, if you want to go to one of the more hardcore languages like C++ or C, Java gives you a lot of the syntax in place. You need to learn a few extra things for those ones. So it's easier than taking it all in, one shot. So Java is it is a serious programming language, but it is not too bad. Your mileage may vary. Anyway, key features of Java. Number one, it is designed to run on any computer, right? It is platform independent. What that means is simply, if you write the source code for a Java program, you can run it on any computer that's Java capable. The other thing, it's object-oriented. We'll eventually talk a little bit about what object-oriented means as well. So Java was originally designed for embedded systems. What embedded systems are, basically computers in devices that you don't think of as being computers. So example, things like your car, there's a lot of little computers in your car, but you don't think of your car as a computer, or smart appliances, stuff like that. So the issue with embedded systems is simply, if you had to design a new programming language for every model of every component in an embedded system, it would be a tremendous headache. It would be really nice if you could just make one program and have it run on any more or less standard type of component. Well, that was the overriding philosophy of Java. That's the niche that it fills in life. Okay, I'm gonna see what we got. We got a little chat here. Okay, some stuff. Okay, great. Okay. So our lecture overview, we'll talk about computer memory and programs, some long-run trends leading to Java, key pieces of Java, and then maybe a little bit of programming, or we might push that off until Friday. We'll see. We'll see how time goes. Okay. So computer memory is basically a sequence of binary digits that are all either zeros or ones, right? The switch is either open or closed. Conventionally, switches are grouped in sets of 8 called bytes, and a byte can hold 256 different values. So any number from 0 to 2 to the 8th minus 1. Okay, so a byte is just a number. Now, computers have two kinds of memory, right? You're probably aware of this. They have random access memory that programs typically run in, and then everything else that's typically for storage. Okay, so the magic of random access memory is you can access any part of that memory in any order at constant speed. So it's great for a program execution flow that has to bounce around throughout memory. On the other hand, stuff like hard drives or, tape drives, if you're really ancient, those you had to spool along to the particular point where your data was, so you didn't want to use that to run programs unless you absolutely had to. Okay, so RAM is the kind of memory where programs run. Now, a computer program is just a set of instructions that's encoded in bytes and stored in memory. So at the end of the day, it's a long series of ones and zeros like anything else, but it's organized in a way that it's easy for humans to build. Now, there's two kinds of programming languages. Low-level ones are very close to the machine's language of bytes that represent CPU instructions. And then you have high-level languages that are closer to human language, which is primarily around words. So something like Java is kind of intermediate. There are people who will say Java is a high-level language, but the question is high-level relative to what? Languages like assembly, which is very close to machine language, those are very difficult for most humans to learn and work with. Other languages that are a bit lower level than Java, like C or C++, allow you to access specific memory locations. In Java, that detail is hidden from you by design. So Java's higher language than some, lower level than others. Anyway, with programming, any programming language, whatever you're writing it in, regardless, ultimately it has to be translated and processed as machine language. The machine doesn't understand what we type, the source code that we create. So it has to be translated somehow. And memory locations where the program is going to run, they either have to be stated in the program, and typically with something like assembly code, you pick the exact locations. You can as well with a language like C. With Java, the memory locations get assigned by the development tools. So for whatever particular machine you have, Java will decide where in memory that's going to run. That process is called compiling. Okay, so why do we run programs in RAM? Well, RAM is fast. Okay, that's the short answer. RAM is faster than any type of other memory for running programs. Other memory types are good for storage, but not for running programs. Now, we talk a little bit about a calculator as a very simple computer, right? So when you use a calculator for multi-step operations, there are going to be memory features, right? Like M+ that adds a value to memory, or mem or MR that reads the value from memory. Well, CPUs and computers are very similar. They have basically memory called registers that are a lot like calculator memory, right? So you can write a number directly into the register, or retrieve it, or have the register write it into some other memory location. So they can assign them values, do simple math, and read and write values from memory, okay? And if you're doing something in assembly code, you're dealing directly with those registers, and I assure you, it's a big headache. I haven't done any assembly code in like 25 years, but yeah, it's a big headache, and you don't want to do it unless it's absolutely necessary. Now, we'll talk about how this works for something simple like assigning values and incrementing, which just means doing a +1 on it. So suppose your program has a counter that tracks how many users are connected to a server at any given time, right? So you have some point in memory where you're going to store that value, and whenever that value changes, you're going to update it. So what do you need? Well, you need a memory location for the counter, right? Some particular memory address in your computer, which is whatever set of little switches, whatever set of binary digits is holding that value. And then you need a data structure for the counter, right? You need 1 or more bytes to hold that value. So in a low-level program, you would first set some kind of reference to the counter's memory address, right? You would basically create some kind of variable called counter and assign an initial value of 0 to it. Then whenever a new user connects, you're going to read the value from counter into that register, add 1 to it, and then have the register write that value back into the counter. Okay, at the low level of the machine, that's what's going to happen. And whatever language you're writing it in, all that stuff remains the same. The part that's different is the part that the human has to write. Okay. Execution flow of programs. So program instructions happen sequentially. So there's a process for how this happens. In our previous example, you would first read the value from counter, then you'd increment it, then you'd write the updated value back, right? That's the sequence. If you do those steps out of order, something's going to go wrong. So when you're doing the execution flow on that, the CPU has a pointer that tracks to the current memory address of the running program. So whatever instruction in memory is about to be executed, the CPU keeps track of that. Okay, and so all of these instructions that are happening at the machine level, they have a fixed size in bytes, and once they're done, the CPU knows to jump ahead to the next instruction at the next memory address. Okay. So there's a little bit of how programs work and a little bit of machine level stuff. If that seemed a little weird and scary to you, don't worry. It's not really something that's essential for programming in Java. It's just a little bit of background that basically everything you do in Java gets translated through a bunch of processes to the machine level. Okay, because we'll have more to say about that in a little bit. So the recap, binary basics, a binary digit is a bit, which is a 0 or a 1. A byte is a number between 0 and 255, and it's composed of 8 bits. As far as programming, computers only understand machine language. All your instructions, all your data are stored in some kind of memory, and the CPU keeps track of the execution flow, but the programmers have to design the data structures, right? Have to designate them to say, this variable is going to be stored at such and such memory location, okay? That's the role of the programmers. Okay, so we're gonna pause this for a moment. let's see. Now, when are we going to do the real programming? We'll start that on Friday. Okay? I mean, we're not just going to roll into programming on the first day. All right. And I don't want people to totally miss the bus, but we'll start a little bit on Friday. Okay. So history about Java. It was released in 1995, so about 25 years ago, designed to support embedded computing. At present, it's still widely used. Part of that is organizational inertia, right? So businesses have a lot of applications written in Java. There's a lot of resources out there in terms of code libraries and in terms of good Java programmers. So it kind of feeds on itself. If a business has these applications written in Java, it's usually much easier to just tweak them and update them than to pull out the whole system by its roots and design it in another language, even though that might possibly be a better thing to do if you were starting from the start. Java also has been the target of numerous security attacks. So there's something with that, but that's not limited to Java. Other, other systems, languages have their own issues. But anyway, Java's out there, it's widely used. So way back when, early days of computing, it didn't make sense to have a language like Java. It didn't make sense to have it platform independent. Why? Because number one, there weren't many computers. There weren't really standard languages out there. If you wanted to program something, you would just flip switches. So whatever kind of model of computer you got, there was a potentially unique set of machine language instructions, which you would set by flipping switches. So because computers were very expensive, the whole operation of programming wasn't something you needed to do very often. It just wasn't. So you didn't have this need for one program to run on a whole bunch of different computers. If a business bought a computer, they were going to take the time to write whatever program met their fairly specialized needs. Now, this sort of tightly coupled system still exists. For example, operating systems. When you get an operating system, it's going to be designed for a particular hardware configuration, right? So Windows runs on PC compatible machines. Mac OS runs on Mac machines, for example. Also, you might do it with high performance computing, right? If you were going to design a particular piece of software to run on a very particular set of hardware, like some cutting edge thing, natural language programming, something like that, that you want to demo at a big conference, yeah, you might develop a special system for that. And in some cases, legacy systems, old systems that still work, but have to be integrated with new technology. So way back when, that's the key point. In the early days of computing, there wasn't really a need for a language like Java. But of course, over the intervening decades, computers got smaller, faster, more powerful, cheaper, and more widely used for about anything you could think of. Now, computers are literally many, many, many million times more powerful than they were, a few decades ago. For example, if you see those old-timey movies of the moon landing about 50 years ago, and they'll have, basically a warehouse full of computers, all that hardware that they have there, the computing power of that was about equivalent to what you could get on a single laptop, something like 25 or 30 years ago. And obviously, so we had, just to talk about the numbers then, I had a laptop in 93, I think, and it had I'm going to say a 25 megahertz processor. Nowadays, right, you get 2 gig, 3 gigs with a lot of extra features that actually multiply that power. So, nowadays for a few $100s, you can buy a computer that's literally hundreds of times more powerful than what they did the moon landing stuff on. So computers, exponentially more powerful than they were a few decades ago. On the other hand, programming very roughly has similar costs, which means, the calculus has totally changed. Once upon a time, the hardware was very expensive, programming was relatively cheap. Now the hardware is practically free, and programming, even though its costs haven't really changed that much, is much more expensive than the computer itself. Okay, so because of that, platform-independent programming become economically viable for a lot of purposes. I mean, you might spend as much to get 1 day's worth of programming work out of a person as it would to buy, a piece of hardware. So you know, like something simple like a laptop. So platform independent programming models are economically viable now. Because why? Because it makes a lot more sense to write the program once and run it on all different kinds of hardware, even if it's not specially optimized for that hardware. Okay, so early on, Java was important for the internet because if you wanted to run applications through a web page, the idea was, well, you don't know what kind of computer is going to show up at the page, so you need a generic language that can run any application we're going to put on there. So Java fit that bill. Basically, you had these little programs called applets that would run in a rectangle on a web page. You would download the application, and you would run it yourself in the web page in the browser. So applets were a big thing in the 90s, and in the early 2000s, we were glad to have them, but they've been pretty much dead for 10 years because there were a lot of security issues. The same things that led to Adobe Flash now, I always say Macromedia Flash, the same things that led to Flash Player going away. Okay, so this philosophy boils down to something called WORA, write once, run anywhere. So Java's design principle is that a program's source code, what's readable by humans, can run on any computer. Now, Java's not the only language that does this. There are other languages out there that piggyback off of the Java virtual machine, but it's theoretically possible for any programming language that has some intermediate layer for abstracting hardware, right? So Java, unlike other lower level languages, Java doesn't interact directly with the hardware. Java sends its commands to the Java virtual machine, which knows where all the hardware details are on that particular machine, memory addresses and such. So if you want to draw a line on a particular graphics screen in Java, you'll send your command to the Java virtual machine. The Java virtual machine will have a map of where the graphics are going to be drawn, and it'll draw it there. In C++, on the other hand, or C, you might have to specifically pick the memory address. In an assembly language, you certainly will have to. You might have to pick the exact memory address and make sure that it happens at the right place. Now, yeah, they've done away with some of that. There are some tools that simplify that process for C and C++, but that's the idea. Java is going to definitely run on any machine. Some of these other ones, you need to pick and choose the particular memory addresses. Okay. Now, having said that, even though Java can theoretically run on any machine, that doesn't mean it's going to run well. For example, you might have a machine that runs great on a desktop-sized screen, but looks terrible on a mobile screen, right? Or you might be missing the input devices. For example, your program might expect that there's going to be a mouse, but if there is no mouse, it's maybe not going to work that well. Other things, memory availability is, of course, a problem. Yeah. Okay. So the primary advantage of WORA is less programming cost and less time required, because time is money. So you can write the program once, it's going to run on any machine. Code libraries, once you write them, we can reuse them on all different kinds of hardware, and hopefully there'll be vastly fewer errors, because every time you write a new program, there's the chance that something goes wrong. Okay. Disadvantages, of course, number one, you're going to need that kind of translation layer in place. And number two, it's generally going to run slower than native code, right? Code that's written specifically for a particular program. Now, it may not be exactly that bad. You can always just have code pre-compiled and it can run on a machine. In fact, that's what they do on some memory constrained embedded devices. But yeah, generally Java does run a little bit slower. It's not quite as efficient as some of these other languages that are designed to run on a specific machine. Okay. All right, so that's it. That's a quick intro to Java. Three key elements: JRE, JVM, and garbage collection. We'll talk about those. So the Java runtime environment is part of the JDK, the Java Development Kit. Basically, it has all the things that you need to run Java programs. So if you grab the JDK off of Eclipse, you install that, one of the things you'll get is this Java runtime environment that will enable you to run Java. And part of the thing that it includes is the Java virtual machine, which maps your specific hardware configuration to the Java language. Okay, so every machine that runs Java programs needs to have this Java virtual machine. It's that translation layer between software and hardware. So for example, right, if I'm pressing K on a physical keyboard, that's going to hit some memory location, and the machine is going to know, oh, you pressed a key. Likewise, if I have a touchscreen keyboard and I press where the key is, the K is where the keyboard, when the keyboard is visible, that's going to have the same outcome. So the Java virtual machine is going to treat a tap on the keyboard with a K the same as hitting that touchscreen K, right? It's going to map to the same outcome. Okay. Garbage collection is a neat feature in Java. So remember I said these lower level languages, you need to allocate memory, allocate and deallocate memory yourself. In Java, you don't. There's this neat little feature called garbage collection that as the program is running, it recognizes what data is no longer being used by any part of the program, and it frees it up for use by other things. So if you're interested, I have a link to how the algorithm works, but I usually don't cover it in any detail because I find that it confuses people more than it helps. The key takeaway from garbage collection is just, if there is some data structure, some variable or set of variables that your program isn't using, Java will automatically get rid of that for you. So if you've ever programmed in a language like C++ where you might have to manage memory yourself, yeah, in Java you don't have to do that. Okay. So quick example of garbage collection. So suppose you run on some server, you have some kind of switchboard application where customers can access their account data, right? They have data in the back and the server exists to help the consumers connect to them. Well, the application is always going to be running on the server, right? 24 hours a day, it's going to be running because customers might show up anytime and want to access their data. Anytime a new customer connects to that server, the application is going to create some data structure that holds the server's account data on there. But customers don't stay logged in forever. So once the customer logs out, the server application is going to discard that customer's data, right? It'll still be stored in the back office somewhere, but it won't be stored on the server anymore. So that's an example of garbage collection that'll automatically happen. Okay, the last stretch of this, so let's do a quick time check. I got to reach into my pocket. We'll do a time check, and we are, how are we at here? Oh, we got plenty of time. Okay, last little bit here we're going to do is object-oriented programming. So Java is an object-oriented language, like I mentioned on one of the first slides in this lecture. Well, what does that mean? It means that things that you create in the program are broken up into objects. Objects are representations of specific things. Now, the difference with this, with object-oriented programming, is basically how data is accessed from outside devices, from outside objects. So I'm going to drop out of this slide for a second, and I'm going to bring up Paint, because it's easier to describe in Paint. Okay. So here, oh yeah, and I got to share it with you, don't I? Let's do that. Let's share it. Boom. Okay. So here I have some application. And over here, some customer object. Okay, so I'm going to draw a box for that. Here it is. And let's say it's a banking application. Okay. Now, when I access the customer object, there's only a few specific things I want to do, right? So here's principle one. Limited set of actions. Okay, so let's say that the basic things I'm going to do with a customer object, I'm going to have two. I'm going to have action one will be credit, action two will be debit. Okay, and I can send along some particular amount. So I can add money to the account, I can pull money out of the account. So limited set of actions. So only these two actions that are defined for this object can actually be done by the program. Okay, only defined actions can happen. Okay, so that's a way of limiting what this application can do to this customer object. The other thing, I can hide information. For example, I can have a balance value, and I'm going to put it in brackets here to show that it's hidden. Okay, every account should have a balance value, but that doesn't mean I should let any application just go in there and directly change something, right? You can imagine that that is a very serious security risk. If I allow any outside application to just, oh, I'm going to overwrite that one with a 1 billion and somehow put $1 billion in your account, right? That would be a very serious concern. So you don't want something like that to be able to happen. Instead, you want to go through specific processes, okay? So you can say, this is called information hiding. I can mandate that some data is only accessed through approved channels, like credit or debit in this example. So what I might do for the credit, if I have a policy in place that I know that there's a limit on how much money can be placed in, right? I might, in that method, I might check for, I might verify it. Let's do that. Let's just do verify the transaction. I might limit the amount. I might say, oh, you know what? If you're trying to put money in through some kind of check or whatever, I'm going to limit the amount to 10,000. If there's anything that's bigger than 10,000, I'm going to say, no, you can't do it through this application. It has to be done by somebody with high-level credentials inside the bank, right? Likewise with debits, oh, it's telling me my internet connection is unstable. Well, that's good to know. Okay, likewise with debits, right? I can prohibit overdraws, right? You can't just take out any arbitrary amount. You can only say you can only take out as much money as you actually have in there. So object-oriented programming, let's do this in red. Object-oriented programming, or OOP, has these features which are very useful when, you know, things like transaction integrity are important. That's not the only thing, but that's a quick and easy thing to discuss here, okay? So with object-oriented programming, you don't just throw together a bunch of code any which way you want. You actually have specific structures that you build one for the application, you build another one for the account object, and you specify all the things that can happen for an account object and which sort of applications or other objects can access that information. Okay, that's the core of object-oriented programming. All right, so I'm going to return back to regular slides then.
I actually had a question.
Oh yeah, go for it.
So when you meant by some customer object, like would that object be, or I don't understand what some
a customer account.
Account. Okay, it's the actual account. Okay, for sure.
Like a bank account, yeah.
Okay, sweet. Thank you.
Sure. Okay. So objects, again, computer code representations of how things act. They include possible actions, which in Java are called methods. In other languages, you may have seen them as functions. Individual and collective parameters, so basically data, which are called data members or fields. And typical objects include both, although they don't have to. You might have some that have one but not the other. So, for example, with a bank account, you would see typical actions like opening an account, processing a transaction, or updating personal information. The kind of data you might hold could be the account balance or the user's name and address. And then you could also have collective parameters that are shared among all bank accounts, right? Things like the interest rate, because typically if it's one kind of bank account, everybody's going to have the same interest these days, probably of like 0%. Or maybe 0.1 if it's, you know, really lavish. Likewise, they'll have the same overdraft fees. Okay, so those, as a matter of policy, you implement them as collective parameters, so they're automatically applied to every object, rather than being uniquely specified for every object, and then they could have differences. Okay. And again, you don't really need to understand object-oriented programming to code in Java, but understanding this will help make things a little bit more sensible. Later on, if you take IDS 401, they're a little bit more focused on how these programs are written up for industry, and then the object-oriented angles become more significant. Okay, but I did want to bring them in. So, other things, a class. So a class is a category of objects. So you could have every object be completely different, but quite often in the real world, you design large quantities of the same kind of object. For example, if you're a large bank, maybe you have 1 million customer accounts. So you build up one class that's going to specify everything that any bank account object would have. And that enforces uniformity among all those objects. So when you create a class definition, you say all of those things have the same kind of data, they all perform exactly the same tasks, and when you write them as source code, you would say a set of methods and data, right? So you'd list the methods and you'd list the data. Okay, now, Java programs are in fact a set of class definitions. The very first class in a Java program is a special one that's the launch point that has a main method. So any class in Java could have a main method, but the main method that you call when you launch the program, that's where it all begins. So I'll give you an example of how the syntax looks. So we're going to, I'm going to pop up Paint here, I guess. Let's do that. I'll do some simple Java coding for you. For example, okay, and then I'll answer questions after this. So if we were going to write up a very basic class in Eclipse, we might do something like, I want it to be black. We might do class bank account, okay? And this is going to say, okay, there's this class called bank account. Then I specify some methods. So I could have void debit. Void just means that the method does not return a value when I call it. Okay, so debit, and I'll say int, and int is an integer value, so a number. I could have a debit method, void credit, same thing, int amount. This is just to give you a quick idea of the syntax. I don't expect people to, you know, we haven't covered any of this. I'm just showing you what it looks like. Okay, so I would have that. I would also have a value here and call that int balance. Okay, so if I'm going to do the debit, I might do something like balance minus equals amount. Okay, and that would just subtract whatever amount was debited from the balance. Likewise, with credit, balance plus equals amount. So whatever I'm adding to the account, that gets added that way. So the point is, I can make this balance hidden, right? So if I leave it like this, it's visible to the outside. Any other application can come along and say, oh, balance is not hidden from me. I can change that value directly. I could overwrite it with a 1 or a 0 or a 2 billion, whatever, any of which could cause severe problems. However, I could make it private and thus seal it off from the rest of the world. And then only methods, that can only be accessed through this. So for example, I might put in a test. I might say, if amount is less than 10,000, right, then do that, right? Otherwise, do nothing. Likewise, I could say, for here, I could say if amount is greater than or equal to balance, then, and only then do I do that. Otherwise, I do nothing. Okay, so this is basically a little bit of the syntax. When you're writing a class like this, you have methods that specify the actions that can happen on that object. You have data fields that specify what sort of data every object of that class will have. That's pretty much it. Okay, and then the rest of it is just learning the syntax. And there's a fairly large amount of syntax, not gonna lie about that, but we got time to learn it. We're gonna spend the first, 5 or 6 weeks of this course learning syntax. Okay, so I'm gonna drop out of this. I'm gonna stop the recording and I'm gonna answer some questions. Okay, so stop sharing, good. And I'm gonna stop the recording and then we'll talk.